Welcome to our first lesson of the grade 11 functions and application course. Today's lesson, we are looking at functions and the quadratic model. Today you'll see a sample lesson and how it looks like and how I use the different graphics to tell you things throughout the lesson. So our first function here, we are given y equals 5x plus 2. And here we have a table of values that we're going to be filling out. Typically the values that I work with for my table of values, I'll do -2, -1, 0, 1, and 2. So I get kind of a range around the y-axis. So now here we'll have and you should get these values for your table of value as well. So now we will be calculating the first difference. And what that means is the difference between the output values in our function. So here we have, we go from -8 to -3. So to calculate the difference, we are going to subtract, but keep in mind when we subtract, we're taking away a negative number. So it'll be actually an addition. So we get 5. Now, 2 minus -3 is also 5. 7 minus 2, also 5. And 12 minus 7 is also 5. So this is an example of a linear function. And linear functions are ones you've been working with since grade 9. And they have a constant first difference. So what that means is they are the same. And here, the first difference is 5, and you can see it's 5 throughout. And a degree of, so if you forgot what degree is, here I have a magnifying glass for our first definition. So degree is the value of the highest exponent of a variable in an expression. So looking at our function, the expression would be 5x plus 2. And our variable here is x, and its highest exponent is 1. So our degree is 1. And that kind of matches with linear. And it has a graph that are graphs that are straight lines. So now we're going to graph this using our points from the table of values here. So I'm going to start. Okay, and that's about good enough for our points. And if you are doing this on paper, please use a ruler, or if you're on a computer, use the straight line, because we need straight lines for a linear function to draw your line of best fit that's going through all these 4 points, and it will be an exact line because it's from the function itself. So now we label our function here as well, y equals 5x plus 2. And you already had the graph, the plane labeled for you with the axes, so you don't need to do anything here extra. But I'll show you later when you don't have the graph how you can start graphing as well. So now moving on to our second function here, we are given y equals x squared plus 10x plus 16, which definitely looks different from the first one. And here you may recall this is called a quadratic function. So similarly, we're going to complete the table of values. So for quadratic functions, typically I test out the values -1, 0, and 1. And if we do this here, I will get, this will be 7, 16. And I see that this is growing from, as we are increasing on the x-axis, my parabola or my function is also increasing. The output values are increasing. So I will actually choose to go from the opposite side and work down from -1 because I want my values to get a little bit smaller. So I'm going to work with these X values, and I highly recommend you pause here and try to get the output values yourself. So I'll take a moment to fill that in, and then you can check back. So you should have received these output values, and I'm actually going to add one more point here, even though it's not in the table of values, and we're going to get this. And you'll see this is going to be important later. So now we will calculate the first difference. So again, I highly encourage you to pause here because we've seen it in the first example and try it on your own this time and see if you get the same answers as me. So you should have gotten these for the first difference. And if we look at these values now here, they're not the same. So we do not have a constant first difference, and that would make sense because this is not a linear function. So now we're going to do one more step and figure out the second difference here. And already, if you're looking at these values, -7, -5, -3, -1, and 1, you should be able to see a pattern here. So let's just confirm that here. -5. Oh, and already we are seeing, oh, so now we are seeing the trend here, which is that there are all two. So now this is an example of a quadratic function. So quadratic functions have constant second differences and a degree of, so if we look at our function here now, x squared plus 10x plus 16, our variable is x, and the highest degree here is 2. So or the highest exponent is 2, so the degree is 2. And graphs that are parabolas. And those are functions that will look like these two. So now I'm going to use these points to plot on the graph. I again will encourage you here to pause and try to graph the points, and I'll check back in for sketching the curve or the parabola. So now I have 6 points, which is more than enough to be able to sketch my parabola. And I hope now you see why I decided to go for that extra -6 point here, because now I see that this was actually my vertex here, and it was our minimum point of our parabola. And so if you're drawing by hand, you're going to be, or even drawing using a device, just try to go through all the points as best as you can, but it will not look perfect, and that's okay for hand-drawn graphs. So now I also forgot to label my graph, so we're going to label. It's always good to label your graph so that when you come back to it, you know what you were graphing. Okay. So now we are given three functions here, and we're told that quadratic functions can be presented in different ways. So these are all quadratic functions, and we're going to justify why they are quadratic functions. So we are going to be doing expanding and simplifying. So let's start with the first function here. So I'm going to start by using my FOIL method, which tells me to multiply the first, the outers, the insides, and the last to distribute these two brackets. So we keep half for now, and then we get x squared and now I'm going to simplify the bracket to get, and then we're going to multiply through the half. And you'll see that based on our definition of a quadratic function, this meets all the criteria. We have a degree of 2, and if you check the second differences, you will see that they are the same. And if you try graphing this, you will also see that it is the same. Um, that it will be a parabola. So when we are given the equation, the thing that we are looking for is the degree. So the degree is 2 here. It's a quadratic function. Check. Now we're going to look at the second one. Here, I will expand this and you will see that it's pretty much the same. We're going to do the FOIL method to get. I will sometimes skip a few steps in my calculations, but as you work through, you should get the same results as me. So our final answers will match. So here we have expanded and simplified. And again, I check. Do I have a degree of 2? Yes, I have 2x squared. So check. This is also true. And finally, for our last function, here, I hope you can just see without necessarily even writing it out that this is just distributing the negative throughout the bracket. And so ultimately you will keep that x squared in there and you will have a degree of 2. So it is also a quadratic function. And we've justified all 3 here. Now, here we are looking at a quadratic model, which is the graphs of our quadratic functions, so how they would look like. So here you are given 2 examples of quadratic functions, and typically our quadratic functions will open upward or downward as we see here. And there are key features that we're going to be looking at throughout this course of these functions. Starting with over here, which is pointing to this point here and also this point here. And these are our x-intercepts. These may also be called roots or zeros. And these are the points where the parabola will intercept the x-axis. And it will not always happen, as you can see with the orange parabola. It does not intercept with the x-axis, and that is okay. That sometimes will happen. And we also have this point here, which is our y-intercept. And this one only has one name. And this would be where the parabola intercepts with the y-axis. You will see both of these have the y-intercept, and all quadratic functions will have a y-intercept. It's just a matter of where they are. And now we look at these dashed lines, and we see that a specific point of the parabola of both of these parabolas is occurring on those dashed lines, specifically these 2 points. And these are called the vertex of the function. And these could be a minimum or a maximum value depending on the shape of the graph. So in the orange graph, we have a minimum because it's the lowest value, whereas in the purple graph, we have a maximum value at our vertex because it's the highest point in the graph. And finally, that dashed line itself is called our axis of symmetry. This line falls on the vertex, or the vertex falls on the axis of symmetry. And what this tells us is that everything on one side of the axis of symmetry is going to be the same as the other. So it's pretty much creating a symmetry within our function or within our graph. And so Again, these are the key features of quadratic functions that we will be looking at throughout this course, and as well as other functions that we will be looking at. So please know this vocabulary. Oh, and the key symbol here is our key concept, so it's important. Please learn them. Now, I have given you an example, and as you see, the page is blank. So I wanted to show you an example where hopefully you have graph paper at home where you can use, or if you're working on a digital device, you can get a graphing paper template to just write on. So I will show you how you can use a blank space or a graphing space to set up graphing a function, a quadratic function. Starting with our table of values, we only need a T shape. And here we have x, and here we have f of x. And again, I'm going to start with -2, -1, 0, 1, and 2. So here we have f of function of x is x squared plus 4. So we will get 8, 5, 4, 5, and 8. And my table of values is done. Now to set up my graph, I start with my x-axis and my y-axis. And the reason I chose this layout like this, because I already know that I'm going to work between -2 and 2. So I have that middle range. But for my output values, I see that they are mostly in the positive. So I don't really need the negatives as much. So I gave more space to my positive integers in the y-axis. So now I'll set up my and maybe I'll spread it out a little bit more since I'm only going to work with these 5 points. And you don't need more than 5 points to graph a parabola. Um, these 5 points will be okay. And now I'm going to set up my y-axis going in twos. And how you pick your scale is really important. So please take a moment to analyze your input and output values and approximately where they arrange to graph your axis as best as you can. So now here we will plot the points. We have 0, 4. And if you're using a graphing paper, this will look a little bit more straight. I'm a little bit approximating it here. And then we will connect these. And finally, I will label my axis and my function. Please do not forget your X and Y to label the axes. I know it's common, but it's good format and good math communication to have these labels. Now determine the key features of the graph. So here we can see the vertex to be 0, 4. And this is a minimum vertex here. It's our minimum value because everything else is going to be greater than this. Our axis of symmetry, so this now is a line. So it will have an equation that will be y equals. Oh, my bad. It will be x equals because we are saying that this is a vertical line that is going to pass through x, and in this case, it's going to be 0 because that's where the vertex is happening, or right over here. So it'll be x equals 0 as the equation of the axis of symmetry. And we will also have y-intercept as 0, 4. And it happens to be the same as the vertex in this case. What are the x-intercepts of this function? This function actually does not have any x-intercepts because it does not intercept the x-axis. As you can see, it's growing upward, so it will never come back down and intercept the x-axis. So we will have no x-intercept. So x-intercept, none. And finally, what is the domain and range of the function? So a little bit of key vocabulary. We will go over this at a later lesson in this course, but domain is all the possible values of our input for a function. And range is all the possible values of our output. But the output is dependent on the input. So we have to start with the input. So here, for a function, the input is all the values of x. And for a quadratic function, you can put any value of x and it will hold true. So x can be all possible values. So, oh, and I'll label how I answer these. We had A there, B there, and C here. And here I will write domain x can be any value. And so later you'll see how we will represent this mathematically, but for right now, this will suffice. So our range now, looking at the graph and based on what we just discussed about the key features, x has a minimum of, or the function has a minimum at 0, 4. So the output values have to be greater than 4. So for our range, we actually have a bit of a restriction. Y is equal to or greater than 4. And don't forget that it can also be, or it has to also be equal to because that's where the vertex is. And of course, any value greater than 4. And there we have our domain and range just in written sentences for now. And moving on to our last question of this lesson, a real world application of quadratics. So a golf ball's height is expressed by the equation h equals 29.4 t minus 4.9 t squared, where t is the time elapsed since the ball was hit and h is the height in meters. And time should be in seconds. So we are asked at what time is the ball at its greatest height and at what time is the ball on the ground. So for this question, and at this point in our course, I will be okay for you to just graph this to analyze and answer the question using graphing tools. So you can just take a moment, go on Desmos, enter this equation and get the graph. And I'll show you my graph and you should have gotten the same graph with these key points. So our first question is, at what time is the ball at its greatest height? So before I even answer that, let me just analyze the graph. So here we have our ball and it starts on the ground. The ball is hit and it works upward, it goes up, 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 and over here it reaches its maximum and it starts going back down all the way at this point where it hits back the ground. So here, at what time is the ball at its greatest height? We see that this is the point where the greatest height happens at 3 times 3 and 44.1 meter. So the height will be 44.0. At what time? The time will be 3 seconds. And at what time is the ball on the ground? Here we have time 6 seconds. And you might also be asked, what was the maximum or the greatest height reached by the golf ball? And you'll be able to answer that based on the vertex. And what would be the maximum height? You should have gotten from the vertex 44.1 meters. From this graph, you can also be asked questions of what is the height of the golf ball at this specific time, or at this specific height, what time was it? So you'll be able to analyze the graph and answer any of these types of questions just from how the graph looks like. So that was the last question of this lesson. So I hope you learned a bit more about functions and quadratic models and key features of quadratic models that we'll be looking at in this course. And if you continue on, you'll see the practice problems here, which you will be completing for homework. It is a review of everything we learned today with some definitions, um, first difference, second difference, a bit of a word bank to practice the vocabulary from today. And some practice with just working with functions for evaluation, just to practice some order of operations, especially if I gave feedback to you from the first prerequisite lesson on some of your order of operations. Please take some time to do these questions. Show all of your work either digitally if you have a tablet or an iPad, or on a piece of paper. And please make sure you are submitting all of your work on the Google Classroom when you turn it in. Follow all the steps in the lesson that is posted. And if you have any questions, please post a comment or send me an email on Google Classroom. You can post a comment on the post itself for that lesson, and I'll try to get back to you as soon as I can. Um, have a great time with the questions, and I'll see you in our next lesson.